Okay, we are back. We are looking at logic gates. We've looked at the NOT gate. All right, that was our first gate there. We looked at the NOT gate, which was a basic transistor circuit. We then looked at the two AND gates, the diode logic and the transistor logic. We did the what? We did all the relevant circuits. We looked at I'm not happy. I don't see my circuits nicely. I would like to take them a little bit up. No. I would like to take my circuits a little bit up, and then okay, so that they are all visible. All right. So we looked at at these two gates so far, the diode logic and the transistor logic and gates. Now what we're going to do is we're going to take any one of the circuits. Let's take the simple one. What we're about here is the explanation. What I'll do with the Z here, I'll connect the NOT gate. So I could connect it there or I could connect it there. All right. So because it's difficult to draw these things, it's easier to draw the diodes. I'll go with the diode circuit. Okay. This is self-preservation. All right. Nothing else but self-preservation. Now you see it's difficult enough to have a straight line, not about trying the circles with the transistors there. All right, there is our, what am I doing? I'm actually trying to draw the DL circuit. Okay, there is my one diode, my other diode, and we know that with this we now have our what? This is basically the frame for the basic frame for the, all right, we are supposed to go to the supply here, all right, but then our Z here, instead of making it an output, we're going to make it an input into the other one. So what we're going to do is basically we are going to, this part is the end, this I'm starting here to do the what? I'm gonna suffer. That guy is not easy to draw. It is not easy to draw. I don't have time to make it look good because it's eating into our video time. So what we're going to do is we're going to basically take going to connect that there, and then we're going to ground. We're going to ground that, and our output is taken here. So we need a supply VCC here and supply VCC, so we might as well make it one VCC. Okay, and there now is our Z. So what we have now is basically the first part. The first part here would be our, the first part this side would be our AND circuit. This is our A and B. Okay, and then that there, as you can see, is obviously our what? Our NOT gate. Okay, this is our NOT gate. So now if we have 0 0 here, it would have given us out a what? Because VCC would have said you've pulled our input, there would be a 0. The inverter will say, okay, is open circuit, so I'm pulling power from VCC. So this 0 actually gives our output as VCC. So if any 0 here, remember we're going to have A, B, and our Z. Right? Remember this part will convert the 0 into a 1. So if we had 0 0 in the input, or any 0 for that matter, what am I doing? 0 0, our output is going to be 1. Why? Because 0 would have given us a 0 here. That 0 is converted into a 1. If it's 0 1, the 0 part is the AND gate will always give us 0, but that 0 is going to be converted to a 1. As long as we're having a 0 here, Now we're having 1, but we still have a 0 on B, so we're still going to have 0 here, and that 0 is going to be changed to a 1. Only when we have both 1s now, this here would have been reversed, and you'd have pulled VCC here. We wouldn't have we wouldn't have a 0 here anymore. We'll have a 1. That 1 will be changed to a 0 by the inverter. Okay, so this is our what? This is our truth table for the NAND gate. So what is this here? This is our AND NOT. So we're saying invert the output of the AND, right? So that part there will have given us A and B. That part there says NOT, but NOT, what's the input now? The input is A and B. Okay, so that is what basically this gate would do. So this here is now our what? Our Boolean equation for the NAND. We said we're going to use equation. We're going to cut it out. Now this here is our truth table. Okay, this is our circuit, but we could have used switches here. What do we do with the switches? We combine. How did we achieve the O with the NAND with the switches? We said we're not going to allow a short circuit. So we say we're going to put a protection resistor, but we said we would have had a what? A short for the what? For the output. Would have had a short for our output with a what? With a NOT. But now the NOT is going to be made not of one switch anymore, but of two switches, which is the what? The two that are what? That are AND. So the resistor here is meant to protect against, if you close both, if you have this state here, you are trying to protect what? To protect your source, so that your source is not damaged by what? By extreme current, the extreme current, unlimited current. So you'll have to have a resistor in series to protect. There's our switch A, B. Together they do the NOT part. Remember, NOT was just a single what? So if we have 3 inputs, we're going to have 3 switches in parallel here, in parallel with what? With the output. If it was 4, then we're going to have 4. So in this case here, we have 2 A and B. So this is our what? This is our switch equivalent circuit. This is our switch equivalent circuit. Okay, so we have our truth table. We have our, the only thing that we have that we don't have yet is what? Is the symbol, and the symbol, our end was a box, a square with, and this would have been our output. But remember, the inverter had a little 0, so our end will have that little 0, so that our output is Z A. Remember, the end is a product, the NAND will be not that product. So remember, because we have 2 inputs, if we had 3, then it was going to be A, B, C coming in. If we had 4, A, B, C, D, and then this here would be what? Will also have to follow suit.